Good morning to all of you. I, Akash Sharma, on behalf of MIDAS IT, welcome you all to this presentation on sword excavation analysis using MIDAS GTS NX. So today in this presentation, first of all, we will start with an introduction to the deep excavation. What is the need for retaining structures? What are the different types? Design process, what is basically the conventional method? Consideration for numerical modeling, like what kind type of modeling, consideration of assumption, geometry of finite element method, soil constitutive model, initial and modified initial ground conditions, construction method, groundwater control, method, etc. Demonstration will basically take into 3D modeling in GTSNX. So deep excavation. Excavating deep for foundation or underground structure is now very common. Maybe it for a tall building or maybe it be for metros. Now, what happens when an excavation failures happens? It leads to heavy loss to life, heavy loss to property, and also increase the duration in the time of project completion. Now, what is the solution to the problem? Now, the solution to the problem of deep excavation collapses. First is use of retaining structure, their proper analysis and design, proper simulation of initial stress condition, and proper simulation of loading conditions. Now, what are the various types of retaining structures? The complexity and the uncertainty involved in design and analysis increase with the degree of soil structure interaction and thus depend on the type of retaining wall which you are going to use. For example, first of all, we have the gravity walls. So in gravity walls, the soil structure interaction is relatively simple. Stability depends on the normal and shear stresses developed at the base. So we have like gravity walls. Now, second is the anchored earth walls. Now, the internal stability of such kind of walls relies on a complex interaction between soil and reinforcing elements. Hence, the soil structure interaction becomes very important to consider. Third is the embedded walls. Now, the stability of the walls rely on the resistance of the ground below the excavation level and on the resistance provided by any props or anchors if you are going to use. So once again, the soil structure interaction becomes very important to consider in such kind of retaining structures. Now, the design process, the conventional method. Now, first of all, what we do is that we select the type of lateral pressure that are expected to work on the wall, whether it is an active pressure, uh, whether it is at rest kind of situation, or whether it is a passive pressure. So we have to consider two things: consider water pressure at poor drainage site, and multiply the pressure by a factor of safety as directed by the code. After that, we apply the external stability checks to ensure the overall stability of the shoring system. So first we have the passive resistance of the system. So the factor of safety against sliding is given by the resisting horizontal force divided by driving horizontal force, and a minimum of 1.2 is required to ensure proper stability of the shoring system. Second is the moment rotational stability of the shoring system. So it is the factor of safety against overturning. This will be basically resisting moments upon driving moments, and a minimum factor of safety of 1.5 is required. So this is all as per the conventional methods which we have used. Also, one need to determine the bearing capacity of the wall. Now it becomes very critical if the wall is based on soil and not rock. Bearing stresses on both the heel and the toe need to be checked. Bearing stresses need to be checked against permissible bearing stresses, and a minimum factor of safety of 3 is required. If not possible, select settlement control is becomes much critical then. Now, to add more checks against failure, which is caused due to failure of soil below the retaining walls, common in regions where we have weak soil strata, and necessary numerical modeling becomes at such sites. Check the shoring system for structural stability, like overturning failure or the bearing capacity failure. So it becomes a necessity to check for individual component the section size, the reinforcement length which we are using. So the accurate forces in the member design for the optimal design becomes important. Okay. So this was about the conventional method. Now let us compare the conventional method and the numerical method. So first of all, the earth pressure in design process. The biggest difference between the conventional method and numerical method is application of the earth pressure. For example, in conventional method, engineer has to calculate the earth pressure and apply the earth pressure on the wall to perform the various checks we discussed just now. So it is good for shallow kind of foundations. But when we come to numerical modeling, the engineer need to create mesh set for ground and wall, assign constitutive model for soil uh, to model the behavior of the soil. Stress and strain are calculated on basis of the constitutive model and external load. And after the analysis, engineer obtain the stress, that is the earth pressure on the wall. And this kind of analysis is more suited for deep excavation as compared to the shallow excavation, which is for conventional method. Now, what are the various consideration when you go for numerical modeling? First, it is important that the correct boundary condition as for the displacement, pore water pressure and loads are applied in any analysis. Now, first consideration is modeling type. Now, in reality, all the geotechnical problems which involve retaining structures are three-dimensional. But when you are simplifying your problem assumption, uh, assumption should be made properly and checked and taken care of to show what kind of analysis you want to go, whether you want to go for a 3D analysis, or if you are going for 2D analysis, the assumption which you made justify the consideration of 2D modeling. So second is the consideration of assumptions. For two-dimensional and axisymmetric analysis, the assumption is frequently made that there is an axis of symmetry about the center line of an excavation as shown in the figure, and that only half section need to be modeled is an axis of symmetry. So at that kind of situation, but as you can see in the right hand figure, there doesn't exist any axis of symmetry. The right hand wall is taller than the short hand wall, and hence we cannot go for assumption considering the axis of symmetry. Third is the geometry of the finite element method. Another decision arises that when you perform the numerical analysis, what is the choice of depth and what is the lateral extent? So what will be the model size which will be accurate enough to give you proper results? So first of all, talking about depth, first is soil stratigraphy often provides an obvious location. For example, if you have a hard rock at a particular location, you can just stop or you can consider that depth as the model depth. Now, since soil stiffness and strength increases with depth, analysis are not sensitive to location of bottom boundary until it is reasonably close to the bottom of wall. Now, as written over it, that when you go down, the stiffness of the soil and strength increases. Now till the model is very much close to the bottom of the wall, it is not going to influence much of our results, and hence we can consider the depth for the model. Second is the lateral extent. So as the excavation is symmetry, the position of the left hand boundary of the mesh is fixed. That is, if you are going for a 2D or axisymmetric modeling. The lateral extent right hand is more problematic and depends on the constitutive model. So as you can see in the figure that how with with the distance from the wall, we have the various lateral extent and the various results can be seen accordingly. So these are the various material models. For example, the highlighted one is Moore column, which is basically the elastoplastic with hardening and softening and ambient influences, and modified Moore column, which is elastoplastic with carp hardening models, which are generally used to simulate the shored excavation model. Now, application of Moore column and the advanced model. First of all, you have for shear failure, we use the Moore column model, use equivalent linear stiffness for compaction or unloading behavior. For nonlinear compaction and shear failure, use advanced models such as hardening models or modified Moore column. Now, application Moore column is used for slope stability analysis, soil structure bonded failure, excavation problems for basic behavior. Now, advanced hardening model for settlement analysis, and if you are going for deep excavation and for detailed behavior. Now, the next point of consideration for numerical modeling is the initial ground condition. Whenever there is excavation, the loading of structure depends on the stress changes associated with the process, and it is very important that these stresses are estimated accurately, and hence the need for numerical modeling arises. Modified ground condition, for example, if you have some building, that what it does is that it uh, change the stress condition in the model, so you must be able to simulate that behavior too in your model, and then once again the consideration for numerical modeling becomes important. Construction method. One need to simulate the construction method adopted using numerical analysis, as it can be for construction stage analysis, because whenever you do a construction, you go for a stage wise construction, and hence to get proper results due to the stress variation because of the uh, excavation done in stages, you have to go consider the construction method opted, and hence one should go for numerical modeling. The next is the groundwater control. At many locations where dewatering becomes very much important, one should be able to simulate that too. So now I'll move on to the demonstration part. So I'll just open a model file. Okay. Now, first of all, what you do is that you start with the geometric modeling. So in the geometric modeling, if you see what kind of elements we have the solid elements, we have the curves. Okay, we have the various curves, and then we need to create the wall member. So I'll just show you the wall right now, stage 1 uh, sheet pile, which will be modeled as a plate element so that we can see the bending moment. Okay, now basically today I will just show you that how you can consider it for modeling part. For example, I'll create a simple model so that I will make you familiar with the commands. Basically what I will be showing you is the following. So if you see that in the modeling part, we have three kinds of elements. First is 3D, which basically encounters for soil mass and the excavation solids. Then you have the 1D elements, which basically if you have anchors, pegs, and beams. Then you have the 2D elements, which are the walls. Now, how we are going to model it? The modeling commands which we are going to use is we are going to use extrude to create solid for soil mass and the excavation solids. 3D line command for anchors and pegs and beams, and extract mesh set command to generate the wall mesh. Okay, so I'll just move on to the program. Okay, so first of all, to move the work plane, you can just go to the left hand side, the work plane. These are the various work planes. So we move on to the XY work plane. Then I go to the geometry. There's are the various tool commands for 2D. I'm selecting rectangle. So it asks me for the input the first corner. So I'm saying it as 0, 0. Input the next corner. So 10, 10. Now the method could be absolute or relative when you have origin as the center point. Otherwise, you have to take consideration what kind of method you are opting. So I'm selecting 10, 10 and say press enter. Say close it. As soon as I click on the isometric view, excuse me, I'll just 0, 0 enter and 10, 10 enter. So when I click on the isometric view, it will zoom fit your model in the screen. Okay. Now basically this is our main soil model. Now we have to create the rectangle which are going to be excavated. So once again, I'm saying rectangle. I'm giving the input location as 4,4 and the relative distance being 2,2. So the rectangle is created. Now let us create the solid. So say extrude. Now, what is your target solid? So if I'm trying to select this outer rectangle, I'm not able to do that. This is because the selection filter says face. I'm making it to basic. So wire selected. Select the direction. So I can select the axis. Reverse direction, the length, let's say 10 meter. Just preview it. Once again, isometric to zoom fit and say apply. Okay, now whatever you create in here goes on to the left hand side. So we have one solid. I'll just unhide it. Once again, select the target object. So I'll just change it to basic. Rectangle selected. Select the direction. And now what I'm going to do, I'm going to excavate it in one layer. Fine, 1 meter thickness. So this is my first stage. Then once again, I can select the bottom. Once again, select the vertical direction. Say preview. Say apply. So you can just create like similarly for different depths. Fine. Now this is our solid. Whenever you create the geometric modeling, don't forget to say auto connect. What auto connect do is that it will perform the boolean operation on all the four solid. So just say okay. Fine. Now if you see the outermost solid, the other solids are cut out of it. Fine. Now this is how we have created the solid. Next, if you remember, we need to create the anchors or the pegs or the beams. Now our work plane is basically XY. So whenever we go to use the command say line 2D, so whatever you want to create will be created in that plane. But what we have in the model is we have anchors which are moving out of the plane. So what we'll be doing is that we'll be using the 3D line command. So select the first point and the relative input you can give, let's say the length being 3. So no movement in the direction of y, and minus 3, say the relative length. So the anchor is created. Okay. Similarly, you can create various line, for example, supporting beams. So you can just say create a line like this or like this. Okay. So this can be a supporting beams. Now, if you want to, you can use commands like translate. Select the target object. So I'm making it, let's say edge. Select this edge. Select the direction. I'm selecting 2-point vector. First point is this and the next point is this. So copy 1 meter, number of times 2. Just preview it. Okay. Fine. So this is how you have to create the various solids and various edges. Okay. Now about the sheet pile wall, I will tell you in the after a few time after we mesh the model. Okay. So having complete the geometric modeling, so for wall you need not create any 2D geometry. Fine. The next stage is you have to define the material. In the material you have to define the various materials which you are going to use. For example, for the beams, for example, we are using elastic, say concrete material properties, the various type of soils. For example, as I told that since we are going for a deep excavation, we have to use the modified Moore column or the hardening model. Okay. Then after defining all the material properties, you need to define the property. And this is basically what kind of element you are going to assign it to. For example, 2D, 1D. Okay. So what I will do is that I'll just show this step quickly. For example, these are our solids. So material, let's say isotropic. I'm just trying to make you familiar with the general workflow. So let's say Moore column, the name is soil. Fine. Okay. So let us define one more property for elastic for basically our walls. I will just name it concrete. So just give it a high stiffness value 0.2, 24. Fine. So just say okay, close it. Now mesh, how to mesh it? Mesh 3D mesh. So we have to define the property. As you can see that since we have not defined the property, no property is coming. So we'll just go to property. So if you remember, we have three kinds of element. First is 1D. So I'll just say beam. So the material is concrete. I'm using the same material properties for everything. For every structural property, say solid round, and you can say 0.6. Say okay. Say okay. So first one is beam. Second, you can create one for wall. So shell element. Let's say wall. So I'm using concrete. Let us give it a thickness of 0.6. Say okay. And the last one is soil. So 3D, give it a name, let's say soil. So you can change, you can see that there are different. So if you have different soil, you have to select soil 1, soil 2 accordingly. Soil, say okay, close it. Now we'll mesh it. So meshing is very simple. You just go to, for example, you start with 3D mesh. So select the objects. I'm just saying select all, give it a size of 0.5. We'll use hybrid measure, soil, just give it a name, soil. Say apply. So after the meshing, we'll mesh the anchor. So I'm just trying to demonstrate you how exactly you define the material properties. So till it meshes. After the meshing, we need to name it. Now naming becomes important because we have to use the various construction stage analysis, and in the construction stage analysis we should know that what exactly which element is. For example, this is my soil main mass, soil 1, which is excavation 1, soil 2, soil 3. So you can keep it if you can recognize it, but when you have very large number of mesh set, you just press F2 and give the name accordingly. Say excavation 1, excavation 2, and excavation 3. Fine. So this is how you can define it. Now to generate the 1D mesh, you can just say 1D mesh. Select the object, say 1, 2, 3, give the number of size, beam. You can just name it as an anchor. So I'm just showing you how to create the 1D element, say apply. Fine. Now we need to generate the wall set. How to create that? So I will be using a command called extract element. So you can see that these are my solid. Now the wall will be basically supporting my excavation, right? Excavation solids. So go to mesh, go to extract mesh. Now geometry type we will select as face. Go to top view. You can just select all the faces. Okay. Fine. Now the properties wall, just give it a name wall and registered on owner shape or object shape. So say apply. So you can see that as many as 11 wall for each face has been selected. I'll just say undo because we have selected registered on object shape. So once again I will select the faces. Fine. Now I'll say registered on base of ownership and give it a name, let's say wall, and say okay. Fine. Now three wall set has been activated, so you can either combine them all. For combining, what you can do, you can just drag one over the other. So the program will ask whether you want to merge. Okay. So once again, okay. So we have one wall set. So this is how basically you create the various elements. You create the solid elements, mesh it for basically for soil. You have the anchors, beam, pegs. So for that you create the 3D line, mesh it with 1D mesh, 1D measure. Then you have the wall element basically which you extract from the faces of already meshed solids. Fine. So let us I will show you that basically now you can see that these are the various stage excavation. So this is the colluvium layer, the weathered soil. Similarly, you can use the extract command for it. Okay, then you have the buried layer. So these are basically your outer soil. Now let us talk about the inner. See, we have named each of the solids separately, stage 5, stage 3 accordingly. Fine. Then this is our sheet pile or sheet wall, which we have extracted. Basically we have used the interface element for it. Now these are all our 1D elements. These are basically the stage 1, stage 2 veiling. Okay, then we have the struts, and then finally you have the anchors, and in between you have the pegs to support the beams. Fine. So this is how basically we do. We have the 3D elements, 2D elements, and 1D elements. Okay, now next stage is we have completed the modeling part. How to define the boundary conditions? So you just go to static slope analysis. You have constraint. There you can use the commands like basic, advanced, or auto. Auto is basically, say, just give it a name GS and say okay. The program will automatically give the boundary condition. Also, if you want to apply some kind of load, for example, you want to define self weight, so just give it a name SW, say okay. If you want to apply some pressure load, so pressure 2D element or 3D element phase. For example, I'm applying on 3D element phase. This I'm applying. So let's say I'm applying for 10 kilonewton per meter square. I'm giving it a load of pressure. So I'm just showing you how exactly you can apply various loads and define the various loading condition. Now next is construction stage definition. How you are basically going to define construction stage. So you go to static slope analysis, you go to stage set, click add, say select this and say define construction stage. Okay, now first stage, as I already told you during the presentation, is initialization of stress condition. So this is the first stage when there is no structural element activated. So this is the activated column and this is the deactivated column. Whatever you want to activate, you activate in the first column, and if you want to deactivate something, just drag and drop and keep in the deactivated column. For example, in the initial stage, we have all this method activated, the ground support condition and the self weight. We are saying clear displacement. So what the program will do is that it will not consider any displacement due to self weight, and only the stress initialization will be done in the model. Okay, save. Now new, the next stage, see, once the mesh has been activated, you need not drag and drop in the activated column again and again, so it remains activated. To see that what is activated, I will just say activate, and you can see that in the model what is active. Second stage, what I'm doing, I'm removing the first stage. Okay, so I'll just hide the solid. So the first stage, it is removed. Save it. New. Similarly, excavation 2. So if you want to activate your excavation 2, say save. And for example, if you don't want excavation 1, you first want to activate the wall, say wall is activated. Then you go to third stage and you say excavation 1 instead of excavation 2. Save it. New. Then once again, if you want to activate excavation 2 and let's say the anchors, so you can activate. So this is how you define the construction stage, as simple as that. Now let us go to the main model. So let us see how our basically the excavation takes place. So this is our construction stage definition. Now let us activate things so that we can understand. So this is our first stage. In the second stage, you can see that the wall is activated. Then in the third stage, we are removing the first and we are activating the strut and veiling to support the excavation. Then excavation 2, 3, and this is our final excavation. Now since these are line elements but they are having beam properties, so what I will do, I will just try to show you. Yeah, with this section it looks like this. You can see that these are basically beams but defined as a line element. So this is how we define the construction stage. Finally, you go to analysis case, general, select construction stage, select the set, and you need to select the first stage as the initial stage for stress initialization. Say OK and generate an analysis case. So after you run the analysis, let us see what results you get exactly. So with each stage, you basically get what is the displacement, what are the stresses. So this is the second stage, so you can see that what is the displacement happening in the model. Okay, and then we'll go to the next stage. Excuse me. So you can see that what is the displacement happening. Even if you want to check that what is the axial force coming in the model, you can check it. Now basically these are the plot of contour. Now how to extract the results? You go to probe, for example displacement. You go to probe, you want to see displacement at any location, you can just click on that particular node, so you can check for it. So this is probe results. Next you have the extract function. Extract function is very useful in construction stage. For example tz, and I want to check displacement at this particular point as a result of all the construction stage. So this is the node number, just say table, and what the program will give you, program will give you results in an Excel format which can directly be exported to Excel and just can be used for report generation. Fine. Now other is iso value surface. This is basically for tz. Now if I want to see the contour plot, so it's basically a pictorial representation of the same. Fine. So these are basically few of the commands. Now I'll just, if you want to see the cell element forces like the membrane forces, you can check for that too. And tx, ty and tz. Now other results, if you want to see, for example the axial forces, the bending moment in the piles uh, or the pegs, you can check for that and hence design accordingly. And if you go to the final stage of excavation, so same results which you can get. So in the beam you can see that what is the axial force. So even in the anchors, if you want to see what is the axial force coming, you can check for that too. Okay, so these are all the results which you will be getting onto. Now moving on to the final part of the presentation, I would like to conclude today's webinar. So in today's webinar, basically we understood what is the design approach between conventional and numerical method. What is the consideration one should keep in mind while performing numerical analysis. So importance of considering showed excavation, modified initial condition, and anchoring and their effects on results, and introduction to 3D modeling with GTS NX construction stage definition. So that's all from our site for this presentation. If you have any query, you can ask me right now, or you can write to us at techsupport@midasit.com. I Akash Sharma on behalf of Midas IT. Thank you all for joining this webinar.